Formerly, he was the head of the School of Medical Science and Technology. His current areas of research include microfluidics, nanofluidics, micro-nanoscale transport with particular focus on biomedical applications, including diagnostic technology. He has been awarded the Santi Swarup Bharatnagar Prize in the year 2013, which is the highest scientific award from the Government of India. He has been elected as a Fellow of the American Physical Society, Fellow of the Royal Society of the Chemistry, Fellow of ASME, Fellow of all the Indian National Academies of Science and Engineering, recipient of the Indo-US Research Fellowship, Scopus Young Scientist Award for the high citation of his research in the scientific and technical journals, and Young Scientist and Young Engineer Awards from the various national academies of science and engineering. He has also been an awards Alexander von Humboldt Fellow and a visiting professor at various leading universities abroad. He has a large volume of impactful publications in top international journals with high citations and a unique expertise in technology development for the underserved population and community healthcare. So now I request Dr. Chakravarti sir to deliver his valuable talk. Please, sir.
Yeah, thank you very much. Uh, Warm welcome to all the participants in this program. I guess they may be either masters or PhD students mostly. So they may be having a reasonable idea of what CFD or computational fluid dynamics is all about. But I would like to talk today about an altogether different approach of CFD, which is based on the phase field model and which is an emerging branch of CFD, although the theory of this has been well known for quite some time. In terms of CFD, this is an emerging branch with a vision to solve very complex industrial problems. And I will today discuss in summary what this model is all about, what are the key features, and some of the very important numerical issues for implementing this theory as a part of CFD. The phase field model picked up its importance in numerical computations in the world of materials. In particular, in the context of fluid mechanics, heat transfer and mass transfer, it has been primarily associated with solidification and melting of materials, which is very much important in the manufacturing industry. While in a large scale you can see that there is a material that is freezing or melting, in a small scale, if you look at the structures, you may get something like the dendritic structure. This is shown here. You may also get different structures like other forms of structures which are not dendritic. You can have equiaxed growth or columnar growth. So all these things can happen. But the important aspect why this dynamic evolution of the topology is important is because whatever fluid flow, heat transfer and mass transfer is occurring across this, that is actually giving rise to the composition of the final solidified material, its microstructure, and hence mechanical properties which are so important for industrial applications. In terms of traditional fluid mechanics, multi-phase flows are very important, and you get lots of industrial applications where in pipeline transport you have air water flows, in cavitating flows, flows in heat exchangers, you get multi-phase flows. More complex situations appear when we are talking about atomization and spray in combustion, and you can see here that in this atomization or spraying process, such small droplets are getting rapidly evolved and they are continuously breaking, coalescing, etc. It is very, very challenging to capture their detailed dynamics. It is so very important because if that dynamics can be captured, the engine can be designed for efficient combustion. And that connectivity between fluid dynamics and combustion is very, very critical. In microfluidics, there are lots of practical applications in industry where droplet generation and droplet transport is very critical. For example, emulsion processing, oil recovery, or the biomedical applications of droplet microfluidics like microreaction, micromixing, drug delivery. These applications are very important. In a more complex phenomenon, if you think of biomedical engineering applications where human body microfluidics is involved, there are complexities associated with the dynamic evolution of, for example, red blood cells, and these are extremely challenging fluid mechanics problems, but very, very important for understanding the rheology of blood and developing disease detection technology. If you think of how to solve these problems, we have to first develop a fundamental physical and mathematical insight of a two-fluid or a two-phase problem in fluid mechanics. Schematically, that is shown in this slide. You have fluid 1 and fluid 2. Without considering any much complexity, let us say that these are incompressible phases and constant viscosity fluid. No other body force is present. So in such simplified conditions, these are the Navier-Stokes equation which are written in the two phases 1 and 2. If there are more complexities, those will be added through more terms in the governing equations. That is not the focus of discussion here. What is an important focus of the discussion is how do you consider the physical phenomenon at the interface. At the interface, you must satisfy the interface conditions. The continuity of velocity, the continuity of shear stress, which is given here, the continuity of normal stress in a sense that the difference in normal stress across the two sides of the interface is equal to the surface tension into the radius of the respective radii of curvature, like 1 by R1 plus 1 by R2. This is well known, and hence we realize that if we have a curved interface, the surface tension is very, very important. But one very important boundary condition that we continue to miss is this one, which is called as kinematic boundary condition. And kinematic boundary condition, this is essentially total derivative of f is equal to 0, where f represents a function of position and time, which is the dynamic position of the interface. So what this equation says is that the total derivative of this function with respect to time is 0. In other words, a particle which is located on the interface will be located on the interface forever. This, in summary, is known as kinematic boundary condition. The challenge in implementing this kinematic boundary condition and the associated other boundary conditions is that the location of the interface is not fixed, but it dynamically evolves. But explicitly from the Navier-Stokes equation or the continuity equation, it is not possible to figure out how this F dynamically evolves with position and time. To do that, there are two broad strategies in CFD. One is moving mesh method, another is a fixed grid or fixed mesh method. In the moving mesh method, grid points are assigned on the interface, and these grid points, they dynamically evolve. You track the grid points, and by tracking the grid points, you can explicitly track where the interface is moving with time. This is essentially what we call as Lagrangian tracking. If this could be done, it is very ideal because exact topology of the interface can be tracked, and therefore it is not or I should say that it is not what should I say, it is not difficult in case you have tracked the interface properly to prescribe the surface tension force at the interface. The greater challenge is that the interface itself may not be stable and it may break up, coalesce, etc. so that these grid points or mesh points which we were tracking, they get completely lost because of mesh entanglement. And then this approach of tracking the interface fails. The alternative approach, which is the fixed grid approach, has a different benefit. The fixed grid approach, what it does is that although it doesn't explicitly track the interface, it uses an Eulerian framework where by a mathematical function it implicitly captures the interface, but the mathematical function is very much similar to the function f that we described to represent the interface mathematically. There are large classes of methods where this Eulerian framework is used, like the volume of fluid method and level set method, and phase field method is one such method. This volume of fluid method or level set method, which I'm sure most of you have heard about, and they are there available with the CFD codes, commercial or open source. These are broadly classified as continuum surface force method, because what they do essentially is they use a mathematical function to find where the interface is and assign a surface tension force as a body force at those control volumes. The phase field method directly does not assign a surface tension force like that, but in a way it also implicitly captures the interface, not as a sharp interface but as a diffuse interface. But the diffuse interface is obtained by appealing to thermodynamics of the problem. This thermodynamic framework is very general and it gives a very nice physical description when the interface width, which is artificial, is comparable to the physical length scale of the problem. For example, if the droplet is breaking up into small, very small daughter droplets, that kind of a situation. So in the phase field method, you start with a definition of something which is called as order parameter. Let us say N1 is the number density in phase 1 and N2 is the number density in phase 2. So if you define phi, which is called as phase field parameter or order parameter, as N2 minus N1 divided by N2 plus N1, then phi is equal to minus 1 when N1 is equal to 1 and N2 is equal to 0, and phi is equal to plus 1 when N2 is equal to 1 and N1 is equal to 0. So what it boils down to is a change in phi from minus 1 to plus 1. This change occurs across an interface, and how the energy of the interface or the energy of the system is related to this phi is you have the total free energy which is driven by the drive. I mean, this free energy is the energy freely available for a thermodynamic change to take place. It is the bulk free energy, which is the free energy of the two bulk phases, phase 1 and phase 2, and this is called as gradient free energy, which is the free energy of the interface. And you can see this gradient of phi is there because gradient of phi is occurring only at the interface. And this lambda is a parameter which is a mathematical parameter, and this actually can be expressed in terms of the physical parameter surface tension. The function of phi, which is the energy of the bulk phase, this can be expressed in various mathematical forms. One popular form is shown here. This is not the only form, but one very popular form. This is called as a double well function, because at phi equal to minus 1 and phi equal to plus 1, this function has two minima, and minima is 0. So that represents minimum free energy, which means that at equilibrium they are stable configurations. So it is consistent with the physics of the problem that at equilibrium configuration the respective bulk phases are at minimum free energy, and that is why they are stable. The total free energy is a combination of these two parameters, the bulk and the interface. Here epsilon is a parameter, it's a mathematical parameter, but physically it is representative of the thickness of the interface, which in this model is a few interatomic layers. From this expression, it is possible to calculate the chemical potential by calculating the variational derivative of this. This chemical potential is important because this chemical potential is a physical indicator of driving force for a change to take place. So for equilibrium, there should not be any gradient of chemical potential, or it should be a constant. For convenience, we can set that constant as any arbitrary constant, and in fact as 0. So if we set that equal to 0, this differential equation we can get, and we can get a solution of the differential equation from here. I will show the solution in the next slide. And then if you substitute the solution for phi and hence function of phi in the expression for free energy, and noting that surface tension is nothing but surface energy per unit area, it is possible to calculate the surface tension, or rather express the surface tension in terms of the two mathematical parameters lambda and epsilon. This expression is important because from this equilibrium description, the parameters lambda and epsilon can be related to the parameter sigma. What is more important or rather interesting in a practical industrial application of fluid mechanics is that the system is not in equilibrium and it is dynamically evolving. When it is dynamically evolving, its free energy is decreasing. That is how a practical system dynamically evolves. It evolves in the direction of decreasing free energy. So if that is done, so you can write this, if you express this in terms of Eulerian variables, it will be capital D dt or total derivative. But here up to this, since it is not expressed in either Eulerian or any special type of variable, we just preserve this small d dt. But when we express this in terms of Eulerian variable, we will use the total derivative. So df dt you can write as df d phi into d phi dt, and that is equal to mu into d phi dt, where mu is the chemical potential. So if this has to be less than or equal to 0, that means mu into d phi dt is less than or equal to 0. In other words, you can write d phi dt is equal to minus of m into mu, where m is positive. Then this product will be negative. And in terms of Eulerian variables, if you express the left hand side, you get a governing differential equation for phi, which is known as Allen-Cahn equation. The advantage of an equation of this form, that it's a convection diffusion form of second order partial differential equation, which is the same mathematical form of Navier-Stokes energy equation, etc., that we normally use in the context of CFD. So to solve this equation, we can use the same CFD template as we use for our well-known other equations. But we also have to consider certain physical aspects. And one very important physical aspect is that although the total mass of the system or for an incompressible fluid, the total volume of the system is conserved by the continuity equation, but individual phase volumes, they are not conserved by some mathematical constraint. So whatever solution we get, from that solution we can obtain the respective phases, and suddenly we can find that some phase has lost mass and some phase has gained mass, although they are not miscible. That means that it's just a numerical deficiency in the CFD that has given rise to that. So some additional constraint has to be imposed on the top of this to ensure a volume conservation, say for a droplet phase, with this additional term. So that modifies the Allen-Cahn equation, original Allen-Cahn equation, with another term, again cast in the same form, but it adds to the complexity of the calculation because this beta parameter has to be separately calculated. And this is known as conservative Allen-Cahn equation. So all these extra calculations you can avoid if you express the governing equation of phi in a general conservation law, in the form of a general conservation law, where the flux you write in terms of the gradient of the chemical potential, and that is where all the thermodynamics is there. And just like diffusion is related to mass transfer, the mobility parameter m, which is again a mathematical parameter, it has, it is not a physical property, it is related to the transport of the parameter phi. So if you substitute the expression for mu, this is the equation that you get, which is called as Cahn-Hilliard equation. Fundamentally, it originates from a conservation law. In that way, it is fundamentally conservative, but the problem is that now we have a fourth order nonlinear equation, and which is normally not there as a part of CFD codes. So what we can do is of course solve this equation and get the phi as a function of position and time, but we cannot use the same template of second order convection diffusion equations like energy equation, Navier-Stokes equation, etc. So some additional mathematical treatment is involved. But if you can do that, which is not difficult because it is standardized, you have a body force which you can include in the Navier-Stokes equation, and this body force you can write as mu into gradient of phi. But this mu is chemical potential, it is not viscosity. So viscosity we have used a different symbol eta. And from this you can clearly see the connectivity of this with surface tension. Surface tension was also an interfacial force which is associated with the gradient of the order parameter. And this is also like that. So, and mu will contain the parameters related to surface tension. So this is a different approach of incorporating surface tension or other interfacial forces in a Navier-Stokes equation by relating the same with the thermodynamics of the problem by coupling the phase field model with the Navier-Stokes equation. And because you have a diffuse interface, all the properties you can interpolate as a function of phi. So this being a very general mathematical treatment, the flexibility of this is that you can add various complexities to make the physical problem very complex. For example, from droplet, which is a fluid-fluid interface, you can go to a vesicle, which is a membrane fluid interface, and then from vesicle to a biological cell, which is a membrane fluid interface with some biological activity inside. So to do that, this is the little bit of change that you have to make in the free energy description, where if you have a membrane, the membrane is like a mechanical entity which has a curvature, which has bending. So all those parameters have to be brought in the calculation. So additional terms for free energy will be there. In addition, there has to be a term which should nullify the surface tension effect, because if you have a membrane instead of a fluid-fluid interface, you do not have a surface tension at the fluid-fluid interface. So whatever terms that we develop because of surface tension, that has to be nullified. Fortunately, the Navier-Stokes equation still can be extended with additional body forces to take care of all these aspects of the free energy, and that particular model is known as advected field model. The whole idea of showing this model is that starting from a very simple problem to a simple fluid-fluid interface, you can actually add more complexity to the problem by adding more terms in the free energy description. If you do that, the entire system of equations, which is the Cahn-Hilliard equation and Navier-Stokes equation, which in the phase field model their coupling is called as Cahn-Hilliard Navier-Stokes equation, can be cast in a generic form and non-dimensionalized. And if you non-dimensionalize, there are three important non-dimensional parameters which evolve. One is a CAN number, which is the ratio of interface thickness to the length scale of the problem. Peclet number, which is the advection to diffusion strength of the order parameter phi, and the capillary number, which is the ratio of the viscous force and surface tension force. These non-dimensional numbers are very, very important to set up the numerical solution, because for any nonlinear problem, and so much so for this type of problem, the model convergence depends on grid independence. And grid independence here is equivalent to CAN number independent solution. That means if you change the CAN number, the solution will not change. And typically of the order of 0.01 CAN number is found to give a CAN number independent solution. This makes sure that the interface is sufficiently thin to resolve the interface. At the same time, it is not unduly thin so that it leads to computational complexities in terms of the large computational time or computational resources required. Now, if you consider the interface region, normally to capture the gradients of the interface, it is a common practice to use 8 to 10 grid points. And if you look at how the order parameter varies across the interface, the variation of phi from -1 to 1 takes place over a non-dimensional length of about 4 into CAN number. This, I mean, from the plot of the function of phi as a function of the interface coordinate, this is what we get. And if we keep 8 grid points, then each grid point, I mean, each mesh size will be 4 divided by 8 into CAN number, or CAN number by 2. So this is the guideline for grid size in the interface. If this is not done, it cannot resolve the physics at the interface. The other important parameter is the mobility parameter. If mobility is taken to be large, then that diffusion will ensure constant interface thickness. So in the way it is good, but the problem is large value of M will lead to artificial loss of mass from one phase and gain of mass in the other phase. So you will see that a droplet which should have a constant volume is magically shrinking. It is not by any physics but a numerical issue. So all these numerical issues can be adjusted by suitably adjusting the mobility parameter M and tuning that with respect to benchmark experimental or analytical solutions, and that typical tuning range is around 10 to the power -5 to 10 to the power -2. This tuning is important because M is not a physical property, so it has to be tuned mathematically. In addition, one big advantage with the phase field model is it can represent the interface or interfacial phenomenon by accommodating the weightability of the surface by using boundary conditions where the contact angle appears as a parameter. You can see here. So in that way, you don't have to give any artificial slip type of boundary condition, but you can directly incorporate the contact angle, which may decide actually whether it is slip or no slip or whatever. Now, what kinds of problems it can solve? Broadly, two types of problems where the interface profile is of great importance, like solidification of alloys, near critical systems, contact line dynamics. And the other is the multi-phase flows where the phase field acts as a numerical tool to simulate the interface, like droplet or bubble dynamics. So these are some model case studies which we have conducted in microfluidics lab at IIT Kharagpur, and I will just show you a glimpse of these examples. All these examples have been worked out as a part of their research programs by my former PhD students who are currently faculty members in different institutes. So for example, this is a problem of evolution of a droplet as it is oscillating in a confinement. It is a very important problem because in human body, the blood flow is oscillatory, and therefore the oscillatory dynamics of any biological cell could be important, and droplet could be one of the precursors. In a microfluidic confinement, another interesting issue is that if you have a sandwich droplet and if you have a wettability of the surface, how the dynamics of the sandwich droplet is governed by the wettability of the surface, given that you have a shear flow imposed on the droplet. So if you have the surface highly wettable, which is given by low contact angle, the droplet phase will like to stick to the surface, but there will be a necking, and a part of that will be separated, but part of the droplet will still stick to the surface. This is called as pinch off. Whereas if you have a surface which is not highly wettable or a hydrophobic surface, the droplet will detach because the droplet phase is not liked by the surface phase. So there will be a transition from this pinch off to detachment, which is governed by many parameters. For example, what is the shear in the flow, what is the confinement, what is the contact angle, and so on. So it is possible through the phase field simulations to get a detailed quantitative understanding of this. These problems were worked upon by my former PhD students, Dr. Devabroto Dasgupta, who is currently an assistant professor at IIT Delhi, and Dr. Kaustubh Choudhury, who is currently an assistant professor at NIT Rourkela. These kinds of problems can be more complex if you apply external fields like electric field. What electric field does is it creates an additional stress at the interface, which is also known as electrical stress or Maxwell stress, and that can influence the evolution of the interface in a very complex way. So this is a problem where there are two fluids and you apply an electric field to move one of the fluids which is conducting, so electric field will directly move it. The other fluid which is not conducting, electric field cannot directly move it, but because of the shear transmitted from one layer to the other fluid will be moving. So this can be a very important technological advantage where you can use electric field to move a non-conducting fluid, which directly is not possible, but indirectly in this way it could be possible. The situation gets more involved if the surface or the surface on which this fluid 2 is there has a pattern structure which gives a variation in the surface voltage and maybe also surface wettability. And in such a pattern scenario, because the velocity will vary along the x direction, you will get these kinds of loops in the velocity profile. And this is a very good benchmark problem because you can also get approximate analytical solution. So we could set up the phase field parameters by coming to a condition where the analytical and numerical, that is the phase field solutions, agree quite well. This problem was worked upon by my former PhD student Dr. Uddipto Ghosh, who is currently an assistant professor at IIT Gandhinagar. The interface dynamics, which is one of the key strengths of application of the phase field modeling, that also can be tuned by electric field. So you can see that there is a fluid A and fluid B. It is acted upon by an external force which is given by an electric field, and depending on the ratio of the viscosity and the applied electric field, it is possible that the interface, the fluid A, in a stable manner moves towards the right by displacing fluid B, and in some case the interface may be unstable and it can break up. And that instability is itself a function of the contact angle at the surface. So we could draw from the numerical simulations a regime of stable and unstable interface. And it is very important, because if you want a practical application to work, you should have a clear understanding that when the interface will be stable and when the interface will be unstable. This problem again was worked out along with the students former students I have already mentioned, with Dr. Pranab Kumar Mondal, who is currently an assistant professor at IIT Guwahati. So with all these examples, what we can summarize is that the phase field model or the phase field method implemented in the form of a CFD model is thermodynamically very rich. The great advantage is that by this model you can couple thermodynamics with fluid mechanics, and therefore the physical aspect of the problem which comes out of thermodynamics can be embedded in the mathematical description through the free energy formulation, and in that way very complex physical systems can be modeled, starting from industrial problems to very complex biological problems and human body dynamics. Thank you very much. It was a pleasure discussing with all of you on this method, and we can take a few questions before we wind up this session and the next speaker takes over.
Thank you so much, sir.
Thank you, sir.
Do you want to ask question? Can ask. We have 15 minutes to discuss.
Okay, so I guess there may not be more questions at this stage. So in that case, I would like to thank all the participants for listening to this very important topic in computational fluid dynamics, which is an emerging topic in the CFD world. Although in the physics world, the physical model has been there for some time, but in CFD it's an emerging topic, and I guess that more and more researchers in CFD will get engaged in working on the phase field model. Thank you very much, and goodbye to all the participants.
Thank you, sir.
Thank you, sir.
Okay, thank you.
Dr. Pratap Pani sir will joining us shortly. Welcome back everyone. Now I would like to request Dr. Pratap Kumar Pani sir to deliver his talk. Dr. Pratap Pani, currently working as professor in Civil Department at IGIT Sarang, and his field of specialization is Field Structure Interaction. He had his Bachelor of Engineering and Master in Engineering from NIT Rourkela and PhD from IIT Kharagpur. He has various research publications in several national and international journals. Dynamic analysis of a floating platform considering fluid structure interaction was awarded by Utkal University in 2018. The slag balls as a partial substitute for India for sand in concrete awarded with Institution Prize 16th Annual Technical Session of Odisha State Centre, the Institutions of Engineers, India. He has attended many national conferences. Now I would like to request Dr. Pratap Kumar Pani sir to deliver his talk. Please sir.
ନାଇଁ ସାର୍ କିଛି ଶୁଭୁନି ତ। No, no, sir, I'm not audible. Sandeep sir, ସନ୍ଦୀପ ସାର୍ ଟିକେ ଗୋଟେ ମିନିଟ୍ ଆସିଲେ, ଏଠି କଣ ହଉନି ସାର୍, ଗୋଟେ କଣ ଆସନ୍ତୁ। ହଁ ଏଠି ଦେଖନ୍ତୁ ସାର୍ଙ୍କର ଭଏସଟା ଆସୁନି କେମିତି।
Sir, we have unmuted. We have make you the co-host. Kindly check your audio system, sir. Microphone, sir.
नहीं तो sir, not audible.
Hello.
Audible, sir. Audible.
Now it is audible.
Audible.
Okay, okay. So we'll start it now. I'll share the screen.
खुल खुल चलता.
Huh? Is this the PPT clear to you? Hello? Hello? Am I audible now?
Yes, sir. Audible, sir.
So is that video, is that PPT clear to you?
Yes, sir. Everything is there. Seen.
Okay. So that PPT is now it is visible on your screen.
Yes, sir. Yes, sir.
Okay, thank you all. Thank you all. So we'll start it now.
Yes, sir.
Okay. Okay, dear friends, we'll see something about this fluid structure interaction, and it is of a floating platform. So let me be very clear. What does it mean? A floating platform, just like your a platform used for offshore exploration, or maybe a large sea, or any other floating platform. Floating platform these days are quite common in some developed countries and some island where it is used for many purposes like defense. So am I audible by this time?
Yes, sir. Yes, sir.
Okay, so no problem. So, floating platform these days, the concept is very new that when we do not find sufficient space, then people adventure into the sea to have different utilities. Okay, so here the what we'll see is we'll see how the fluid interacts with the platform or a plate. And to begin with, we'll see the frequency. Generally, in structure, what we see, it is the frequency which is an important thing. You must have heard about resonance like that. If the applied frequency or the force coming to the structure or the plate or the platform matches or comes closer to its natural frequency, then disturbances are too much. So always it is tried to keep the applied frequency away from the fundamental frequency or natural frequency of the structure or the platform. Okay. So basically your seminar or your course is on transport phenomena of fluids. So here what we are doing, we will consider much of the fluid part, and in this type of problem, the movement of the fluid is not that much as we see in other cases, but interaction is high. Are you clear? Hello? Are you clear about this?
Yes, sir. Yes, sir.
Really, you should reciprocate so that this discussion will be a good one. Okay.
Yes, sir.
So
Yes, sir.
question is, this type of problem, the movement of the fluid is not that much as we see in a river or canal or whatever may be in your chemical engineering, where flow will be more, velocity is more. But such type of problem which we'll discuss here is a little different one, where velocity of the fluid is not that much, but its impact is very much. Are you clear about this? Okay, so here we will see about such type of problem. Now to begin with, what we'll assume that the fluid is invisible, that the viscosity part of the fluid we are not considering at the beginning. Compressibility of the fluid we are not considering at the beginning, that is fluid is invisible, incompressible, and having small amplitude irrotational motion. Is it clear? Hello, is it clear?
Yes, sir.
Okay. So I have that platform I have considered as a rectangular shape, which is made of a homogeneous material, so that it follows the Hooke's law. And what I am doing is, I have applied finite element method for the solution of the problem. And in application, in engineering application, always we go to the solution. This is the problem and this is the solution. To find the solution is the basic aim of an engineer. So earlier what we are doing is, we are doing only mathematical calculations, that is analytical, mathematical differential equations, partial differential equations, those things we are looking into. Gradually, these numerical methods have taken the place, and from so many numerical methods are there, but the robust one and a traditional one everybody can use is your finite element method. Okay, so here what we have done is, the fluid domain, that is below that floating platform, that fluid domain, which is basically water body, maybe a ocean body. So the fluid domain, most of the researchers, they use that velocity potential. Okay, but here we have not used velocity potential. We have solved it in another way, because my velocity may not be that high or may not be of appreciable amount. So if I use velocity potential, what happened? During this numerical handling of the problem, that locking problem, there comes a locking problem. That is, the problem will not be solved, rather it will be locked. Such type of problem. It is something like in our simple arithmetic, as we do division by 0, it becomes infinite. We call it infinitely large, but it is not, may not be infinitely large. It is indeterminate. That is, I stopped there. Okay, are you clear?
Yes, sir.
Okay, so here what we will do is, for problems of this nature, I have considered pressure as the nodal variable instead of the velocity. Okay, you can see the PPT line by line afterwards, but here I have taken the pressure as the. Here you can see, are you able to see the diagram? Hello?
Yes, sir. Yes, sir.
Okay, okay. You see the top, what I have done is, here a plate is floating. Think of a wide platform as you see in some TV. So that is just like in an ocean, a platform is floating. Then you may ask, what is the utility of the platform? As I told you, the platform may be used. These days, it is used in a wide variety of ways, starting from defense requirement, where naval base is there, a floating naval base can be there, a recreation park may be there. Or sometimes nuclear plants, people, countries like Japan, they are planning to have the nuclear plants, nuclear power plants inside the ocean over floating platforms, so that in case of disaster, only very few casualty will be there. Okay, so here is this floating platform. It is the depth of the fluid or liquid is h, and side of this platform thickness is very thin, t, and the plate size I have considered b, width l is the length of the. So different types of shapes can be taken. Here I have taken a rectangular one. Is it okay? I have considered a rectangular plate to be a simple one. Oh, is it clear now? Hello?
Yes, sir.
Yes, sir.
So far what we have considered is, we have considered a rectangular plate floating over the sea, and I want to find how the natural frequency of the plate is affected by the fluid domain. That is, the same plate, if I keep it outside, that is in air or in vacuum, if the same plate is put over the ocean surface, is the frequency is varying or not? Clear? So in the analysis, what I have done is I have considered the fluid domain below that plate to be three-dimensional. A three-dimensional fluid domain I have considered, and for the plate I have used, there is so all people are from chemical engineering or people from other discipline like mechanical, metallurgy, or like that civil are there? Hello?
Sir, from different discipline, chemical, civil,
Okay.
mechanical.
So mainly from chemical metallurgy.
Yes, sir.
Okay. So I will help you. So what I have done is that platform, it is just like a plate, and that plate bending theory is utilized to model the plate, and fluid domain is separate, plate domain is separate. In earlier researchers, what they have done is they have used a coupled problem, that is fluid and structure combined. In that case, the interface that some problem occurred. So what we are doing here is to make it more simple, we have decoupled it. Fluid is separate, plate is separate. Clear? The plate is providing an acceleration to the fluid domain, and the fluid is giving pressure to the plate. Yes. Okay, minute. So this I have used this Mindlin's plate bending theory. There is a theory called Mindlin's plate bending theory, and that I have used. There are some other theories like your Kirchhoff's plate theory, but Mindlin's theory have been used only to take care of the shear in the plate. So generally for thick plate, we are using this Mindlin's plate bending theory. Okay. Now, before I use this numerical method, always this theoretical formulation should be there. That based on this mathematical formulation I have used, please hold it just half a minute. Okay, sorry for the disturbance. Okay, we'll continue now. Okay. So this theoretical formulation, you see here I have used. Now you people must be very clear about this continuity equation. Are you able to listen me? Hello. Are you able to listen me, you people?
Yes, sir. Yes, sir.
Okay. Really, since I'm presenting from this PowerPoint, really I'm not able to see you people. Okay.
Yes,
so this you see this first equation, what is written this 5.2.1. So this numbering you forget. You see this one. This first one is your continuity equation. The second one is your conservation of momentum equation in fluid domain. You people must be clear about these two. Are you clear about these two equations?
Yes, sir.
Please be sure, or I will otherwise I will explain what it is. Should I explain or you know it? Okay, anyway, this continuity equation, you see, this continuity equation, this is the general continuity equation. Then I will simplify it. That is, it is varying with this density. You see, this rho is the density. This density, it is varying with time, but afterwards we will make it incompressible. So this term will not be there. this conservation of momentum, you see, it is written in index form. It is written in index form. That is, suppose the second term you see del rho by del xi rho f uj ui like that. That is, it will cover all I and j, and I and j should not be same for the term. Suppose three dimension element I will take, then uj ui will, that is, let us say j is 1, then I will not be 1, it will be 2 and 3. That is u1, u3, another term will be u1, u2. So for that, you follow any standard find element book, you can get it. That is, you see here I have written in j direction. I have considered a direction j. In j direction, this is the, in j direction, this j may be 1, 2, 3. Suppose 3 dimensional, if j is 1, then all j will be 1. And I will be 2 and 3. If j will be 2, I will be 1 and 3. Is it clear? Hello?
Yes, sir.
And no one is responding.
No, sir. Everything is okay.
Okay. So otherwise, what you can do is, you see any fluid mechanics book, this equation, continuity equation and conservation of momentum equation are there. So based on these two equations, we have gone forward. Okay. So when I will consider, when this fluid to be inviscid, that is viscosity part, I have not considered in the beginning. We have done the analysis for viscous flow also, for viscous liquid, for compressible liquid, everything. For the beginning, let us say there is no viscosity, fluid is incompressible. Then in that case, these two equations will reduce to your Laplace equation in pressure. In pressure terms, this del square, what does it indicate? That is, this is del dot del p, that is dot product of gradient of gradient. Is it clear?
Yes, sir.
So this is, we call it the Laplacian operator, del square. So now that converts to del square p equal to 0. We call it Laplace equation. This p is the dynamic pressure given by the fluid to the platform. Okay. So now this del square p equal to 0. This is the basic equation. This equation will be solved with different boundary conditions. The same equation will give different results for different boundary conditions. That is important. In a differential equation, boundary conditions are important. Okay. These boundary conditions are this. That is the free surface of the fluid. Suppose plate is there. Beyond the plate, it is the free surface of the ocean or tank, whatever it may be. Clear?
Yes, sir.
So that free surface, what is the boundary condition of a free surface of the liquid? That is the gradient of the pressure along the normal direction, that is del p by del n. It will be what? It is in the along the z direction. So I have converted into del p by del z. This is what? This is p double dot by g. That is p is the dynamic pressure. That is how the pressure is varying with time divided by g. Okay.
Yes, sir.
Okay. And the fluid structure interacting part, where the fluid is interacting with the fluid. Then here this normal, the gradient of the pressure is minus rho f by a, where rho f is the density of the fluid, a is the acceleration of the plate. Is it okay? Think of a plate, just it is floating on water, the wave is there, or if wave is not there, then the plate is pushing the fluid at one point, at the other point it is coming out. If the plate is rigid, then there will be no bending, it is different. But since it is a large plate, whatever may be the thickness of the plate, I will consider it to be a flexible one. Okay. So then let us say the force high, the fluid domain you consider. Go to that third slide, where the below that platform, the fluid up to the ocean bed. Okay. Then all the four sides of the fluid domain, what I consider, there is no variation of pressure along the boundary. So del P by del N equal to 0 along different sides, you see. Del P by del N 0, del P by del N again, here Y is 0, it is X, B, Z, that is the one width, the other one, it is the L, B, Z, X, Y, height is Z. And the bottom surface again, bottom one, I have considered it to be a rigid one. So it is del P by del N is 0. Del P by del N will be 0 if the boundary is a rigid one. That is, the wave will return back from that place. Okay, this is about the wave part of the fluid. The next what we will do is, this is the equation del square P equal to 0, and these are the boundary conditions. Based on these boundary conditions and equation, we will solve the equation by finite element method, and we will get the result. Is it clear? Yes or no?
Yes, sir.
So I think many people know what is a finite element method, or you have no idea. I think finite element is taught at the degree level in mechanical engineering, civil engineering, as I know. So during master's level, you people must have some idea about boundary element method or finite element method, the basic one. So what we do is, in finite element method, the total structure we make into small parts, units. It is just like a wall made up of bricks. Similarly, the total structure is discretized into small units called elements. And in the fluid, what I have considered 8 loaded elements. At the corner, 8 loads. It is just like a brick shape. So many people call it a brick element, but it is a 3-dimensional element. Technically, it is a 3-dimensional element of the fluid. And at each corner, the pressure, let us say Pi bar. So inside the element, the pressure P will be, there is a function called interpolation function, Ni Pi. So for 8 nodes, there will be N1, N2, N3, like up to N8. So the pressure inside the element will be summation of Ni Pi bar. Ni Pi bar are the interpolation functions and nodal pressure values respectively. Okay. Then to solve that using finite element method, this del square P equal to 0, this del square P, that Laplace equation, I have converted into that weak form of, and which method I have used? I have used Galerkin's weighted residual method. I think this Galerkin weighted residual method, you people are reading in your numerical methods in engineering, maybe in 7th or 8th semester, if people are reading. So all of you are, have some idea about Galerkin's method? Hello?
Yes, sir, audible.
It is audible. Okay, fine, thanks. The question is, how many of the participants know about what is Galerkin's method. They must have read it in BTech level. Okay, anyway, the use of this Galerkin method, it is called weighted residual method. That is, different nodes will get different weightage, and for that, it is written in this form. This is N is the interpolation function, T is the means transpose. So N transpose del square P 0, where lambda refers to the total summation, and this lambda E, it is for the element. And if I use this finite element method, I will go to a form like this. That is GPB. G, this is the mathematical formulation. B is the summation of all boundary. That is the this Galerkin weighted residual method converts this equation to a weak form of the solution, weak form of the differential equation we call it. And that weak form of the solution, from that weak form we will get the solution. This weak form, this word weak does not mean that the system became weak or the equation became weak. It is the name only. Okay. So this boundary conditions. This is the free surface. This is the fluid structure interface. That is the platform is over the fluid. That is called fluid structure interface. This is the boundary, the sides. Sorry, base. This is the base of the bottom of the fluid. This BS is the sides. So putting these boundary conditions, I will come to a equation like this. Then this EPG, okay, this EG dot P double dot. Then we will come to the structure part. That is the fluid part, then the structure part. I will consider, at the beginning, it is on-damped free vibration of the platform. This is M x double dot plus kx is 0. M is the mass matrix, x double dot the acceleration of the plate, or the K is the stiffness matrix, X is the displacement matrix. It is the 0 matrix. Okay. This is the form to get the free vibration frequency of a plate. Then this fluid is changing these conditions. So if I will put it to the fluid part, the resulting equation I am getting in this form. One is mx double dot kx, then the net result is, it will be this RFS transpose. This term is your connecting term. And finally, I will get the equation in this form. This dP, it is the property of the plate. We call it the bending coefficient. And this lambda or omega, this omega is the non-dimensional free vibration frequency. This non-dimensional free vibration frequency we want to calculate. Okay. Okay, this part, this mathematical part you go through. Then we will come to this one. We combine it together. Finally, we will obtain for when this free surface wave is not considered along the top surface of the fluid, waves may be there. Now, if waves are considered, again, it is the next phase of the analysis. But at the beginning, to make it very simple, fluid is inviscid or non-viscous, incompressible. Suppose I consider a very low density fluid. I can make it compressible. Suppose air. Air is also a fluid. The flight is moving, or then I can consider it to be very compressible. Similarly, there are some fluids where compressibility should be taken into account. Or suppose a liquid container, hazardous container is there of containing chemicals, and there is earthquake. Then the vibration of the liquid, there I have to consider the compressibility of the fluid. Though the liquid may be gasoline or any other chemical, it is incompressible for a general force, but when earthquake will be there, then the little compressibility will have a disastrous effect. So I have to consider the compressibility of the fluid. So, but for the beginning, I have considered the fluid to be incompressible, non-viscous. Okay, so in that case, the final equation I will get in this form. From this, I can find the free vibration frequency. Based on this, I will get the result. Okay, that is plate. You see, this. You see, there is present investigation in air, present investigation floating on water. Then some earlier researchers, they have done it in air, they have done it in water. Okay, so experimental values they have got, theoretical values they have got, both in air. But here we have considered the theoretical values both in air and water and compared with the experimental values of those people. Just one minute. No, sir. No. Hello, sorry for the disturbance. Are you able to listen me again? Hello.
Yes, sir.
Okay. I was disturbed a little bit for this office job. Okay. Now you will come to the result. You see this black line. This black line is the experimental result. It is done by this Mariosi and Sergio. Okay. And this red line is their theoretical values. They have the theoretical values and it is their experimental values. And this green line is our result. Okay. So to the experimental values, their theoretical result is approaching from the upper side, or we can call it a upper bound solution for the experimental one. And our result is a lower bound solution to this. Okay. If we make the element thin and thin, it will approach it. Then question is why our result is not coming from the top side, from the upper bound solution. It is because of the difference in approach. They have considered a boundary element method. We have considered finite element method. Okay. Then that mathematical handling of the problem is like this. Okay. Now you see, we have considered the free vibration frequencies of different widths to fluid domain. That is, if I consider the different widths of the fluid domain, that is, you see this B dash by B, it starts from 1, then gradually I have increased 1, then I have increased it. Okay, this omega 1, omega 2 is the first fundamental frequency, this is the second fundamental frequency. That is, ask the if I consider, you see 1.4 is this, that is beyond 1.4 times or 40% excess, 40% excess. In those cases, if I consider the fluid, suppose my plate is, let us say 100 meter by 100 meter, large platform. Then if I consider the top surface of the fluid on the ocean 150 meter by 150 meter, then whatever result I will get, if I consider 1 kilometer by 1 kilometer of the sea surface, I will get almost the same result. That is the logic. That is how far I will consider. Because this is a numerical method. So to get the advantage, I have to see which amount of fluid width beyond the platform I will consider. It is also practically clear. Suppose you are looking a boat or a ship or a submarine, whatever it may be. Then beyond that, the effect of the submarine or a boat or a ship is generally seen up to 2 times, 3 times. Beyond that, the fluid is not disturbed. So these are the conditions up to what I will consider the width of the fluid for my analysis. So let us go to the frequency. The first 4 frequencies I have considered. Okay. Then effect of flexural stiffness of platform on free vibration frequency. That is, if the plate is more flexible, then effect is more. If the flexibility, if it is a thick plate, the effect is not that much. Okay. The higher percentage of reduction in lower frequency is because in lower, okay, here you can compare. You see, depth of the fluid I have considered and how these frequencies are there. This is the experimental and this is the value I get. Okay. Comparison of free vibration frequencies for with and without consideration of surface wave. This consideration of the surface wave, it is important, but I have not shown the detailed mathematics. Simply you see the result. That is, when I consider the surface wave, the free vibration frequencies is little less. You see, it is considering the surface wave. It is without considering the surface wave. Clear? Here it is. That is, it is that consideration of surface wave reduces the free vibration frequency of the platform more than the case when the surface wave is not considered. Okay, thank you. So my whole endeavor is to give you some idea about how a platform behaves over a fluid, where the movement of the fluid, the pressure in the fluid, the wave formation on the fluid affect the structure. We call it a fluid structure interaction problem. Okay, are you able to listen me?
Yes, sir.
Okay, you people, you may unmute your system and may interact with me. Anything you want to know from me. Really, it would have been better if you people could have stopped me in between what it is and how it is going to be. Really, detailed mathematics you may not know, but the overall idea how a platform over a open sea or is behaving. Okay. Hello.
Yes, sir.
So some people should ask me something if they want to know about this floating platform. Really, these you people, I think I do not know whether it is these days shown on TV. There is a TV show called Mega Structures. Okay, Mega Structures. In mega structures, you will see such type of structures in the ocean, or we call it offshore structures. Offshore structures means they are floating in the sea, and the size is very, very large. You just think of a power plant like our TTBS thermal. Okay, are you able to listen to me?
Yes, sir.
Yes, sir.
Okay, so such a plant is floating on the sea. In Japan, power plants are there which are floating on the sea. So how they are able to do?
Yes.
Okay.
Okay, sir.
So anybody who want to know something from me? No. Okay, thank you all. Thank you, friends.
Thank you, sir.
Thank you, sir.